Okay, so yesterday we were discussing about the working principle of photovoltaic system, then the photovoltaic effect, how the potential difference is created when a PN junction is formed, and what is the gap potential that has to be overcome. Such things were discussed. Today we will discuss about the components of PV system. We are going to discuss each of the components of PV systems. So before going to the different components of PV systems, we need to know what is a PV module, then a solar cell, then a solar panel. So the smallest component is solar cell, that I'll first, which is a crystalline solar cell that is normally represented like this. And so this is a solar cell. Now if such solar cells are connected either in series or parallel to form a PV module, then a PV module is like this, where you will have several solar cells. Okay, like this. This will be a PV module. Now, if such PV modules are electrically connected, multiple PV modules are electrically connected like this, then we say it as a PV panel or a solar panel. Okay, now if such PV panels are connected in either series or parallel or different series parallel combinations to form a PV array. So this is one such block. If they are connected in series and parallel combinations, then you can form a PV. So this is a string of panel. Okay, a string of panel forming a PV array. Now let's see what is the effect of connection of panels in series and parallel, or cells, solar cells in series and parallel combinations. So let's see this. This is a solar cell. Okay, this is a solar cell. This is another one. So I have two now. So say I have the open circuit voltage of one solar cell as 0.6 volt. And if I am connecting these two cells in series, then what is the total voltage? What is the total voltage? If I am connecting like this, then so here, see, if I am connecting three, see, I'm connecting three such. Okay, like this, if I am taking this, VOC will be for one solar cell, it will be 0.6 volt. Now I have connected three solar cells, each of which each of which having the VOC as 0.6. Now the total is, I'm taking from here. Okay, the total is here, which is 0.6 into 3, which is 1.8 volt. Now, so this is series connection. Now coming to the parallel connection, how will you do parallel connection? So what is the importance of parallel connection? The voltages will be same and the currents will add up, right? So I'm connecting like this now. Connecting like this. Okay, like this I'm connecting. So if what will be the voltage here? What will be the voltage if these three cells, the same three cells are used here for parallel connection? Then
0.6 volts.
Yeah, 0.6. Yeah, so this will be 0.6 volt. So this is what is basically the series and parallel connection of different cells. Now let's see the VI cara of the I'm calling it as IV cara, okay, because the current is in the vertical axis. So current I in amperes, here voltage V in volts. Okay, now so IV cara I'm drawing like this. Okay, so say this is 0.6 volt. This is the current. At this point, current is ISC. ISC. What is ISC? Short circuit current. At this point, this 0.6 volt is VOC, the open circuit voltage. So when it is short circuit, what is the voltage? It is 0, right? So that is this corresponding to this point, current point, this voltage is 0. So this is the current voltage cara. Now these three are, see, suppose I am connecting in parallel. This is for parallel connection. Parallel connection. So for one cell, if the ISC is this much, this will become, if two are in parallel, then this will become 2 into ISC. Right. If three are in parallel, this will become 3 into ISC. But voltage is still the same, this 0.6 itself. Okay, now when you connect in series, how will be the voltage current cara? Again, current I, then this is voltage. So this is one IV cara for one cell. This is ISC. This is VOC. Now I am connecting one more in series. So ISC won't change, but VOC will change. This will become 2 into VOC. And another one also I am connecting the same unit. So this will become 3 VOC. Still the ISC is same. So this is series connection. Okay. Now let's put some numbers to get a better idea. So so for a total module, the voltage and current output can be tuned by arranging it in different combinations, different topologies, series and parallel combinations. Because if the standard voltage is higher, accordingly we can connect cells in series. If the current rating of the load is high, then or if we need a higher current output, then we can connect them in parallel. Okay, so basically it's a series parallel combination. Now a typical PV module, we'll see a typical PV module containing 36 solar cells connected in series. So I'm drawing here a PV module like this. Okay, like this, in which 36 here. So I have 9 rows. Okay, 9 rows. Each row has 4 units, like this 4. Okay, so total 9 into 4 equals 36. And all these 36 are connected in series. Okay, all these 36 are connected in series. So the connection is like this. Okay, they are connected in series. Then what is the total voltage now? If for one unit, if for one unit, if it is 0.6, VOC is 0.6 for one cell, solar cell, then the total VOC, the total module output, what is the total module output?
The 21.6.
Yeah, so total module VOC, I am writing module VOC equals 36 into 0.6 equals 21.6 volt. And what is the ISC? If for 1 unit it is 5 amps, then
5 amps.
5 amps. 5 amps. Okay, good. Now, I am trying to do the same with the parallel combination. Then I'm using two strings here. Two strings. So 2 strings of 18 series connected cells connected in parallel to another 18 series connected cells. Okay, so I have 18 like here. Okay, 18 series connected cells connected in parallel. Okay, to another 18. Now can you find the module voltage output and module current output? What is a module voltage output?
10.8, sir.
Yeah, so 18 into 0.6 will give you the module voltage output, which is 10.8 volt. Then what is module current output? For this 5 amps, then for this 5 amps, both are in parallel. So 10 amps, right? 10 amps. So basically the IV characteristic of a module consisting of M identical cells. Here we have only used identical cells. It's for M identical cells in series and N identical cells in parallel. So in general, if M identical cells are in series and M identical cells are in parallel, then how will you find the module output? The voltage multiplies by a factor M, right? The voltage multiply by a factor M and the current multiply by a factor N in general, right? For the module, Okay, so this is what we do with the series and parallel combinations. Now this is just PV module. With these PV module, if we form a PV system in the sense it will have load, we should feed the load, then an inverter would be there to, if the load is AC, then we have to convert the DC power output of the panel to AC. Then if you need to power the load at night also, then what will you do? You have to install a battery, right? You have to install a battery and the charging and discharging of the battery should be controlled. If it's a standalone system in the sense it's not grid connected. If it is grid connected, then grid will also supplement the power, the feeding of the load. So at night you can use grid for power supply, or if it is not there, you can you should completely rely on the battery. So PV systems basically PV systems. So if a whole house should be powered, then the system must be operational day and night. If it is in the standalone mode, that means if it is not connected to grid. And it also may have to feed both AC and DC loads, because sometimes you have DC loads, sometimes you have AC loads. Both must be powered. So depending on the system configuration, 3 main types of PV systems are there. First one is standalone. Second one is grid connected, and the third one is hybrid. Now let's see what is this. What are these topologies? Okay, PV systems. So the first one is, I'm writing here a standalone system. So I have a PV module. I'm not going into the detail. I'm just writing here this PV module. Okay, PV module. and I'm connecting this to, I'm feeding a water pump. Okay, a water pump, and water is pumped to a reservoir, some reservoir. Okay, so this is a DC PV system which powers a water pump with no energy storage, no energy storage, which means here whenever sunlight is there, it will pump. When sunlight is not there, it will not pump. That's all. You don't need energy storage here. You are just doing it as and when it is available. The natural resource is available. But in contrast to this, you can have battery storage with a complex PV system, including this power electronic, some power conditioners, inverters, converters, etc. if you have both DC and AC loads. So with the same PV module, what you should do is, in this case, in the case in which you need you need to power both AC and DC loads, you need battery. If it is not a grid connected mode, because this is standalone, I'm not considering grid here. So I have, from the PV module, I am going to the charge controller, then from the charge controller, I have directly from the battery, the output of the battery is DC, so I can power DC from here. But if I want AC to be powered, AC loads, these are DC loads. If I want AC loads to be powered, then I have to convert the output DC of the battery to AC. So I need an inverter here. And the output of the inverter is AC. So I will power AC loads through the inverter. Now, from the charge controller, I am controlling the charging of the batteries. I have batteries here. So I have battery here. It can be a collection of several battery units. I am writing just a battery. Okay. So the charge can be controlled accordingly. Why we need a charge controller here? Because when the battery is full, it should not be charged beyond that point. So the charging process should be stopped, right? And if enough sufficient sunlight is not there, then how will you power the DC and AC loads? From the battery will discharge, and through the inverter it will power the AC loads, and through the charge controller directly from the DC power output of the battery, it will power the DC loads. So the discharging and charging is contextual. It depends on the sunlight that is available, or directly we can take through the battery also. With this sunlight we can take, and if the battery state of charge is low, then you can charge the battery. A part can be used to charge the battery, a part can be used to feed the loads, because we don't have a grid connection here, grid supply here. So it has the battery size should be accordingly planned or designed. Okay, now if we are using grid, then what is the difference? So for a standalone system, it depends on solar power only. These systems can it can consist of PV modules and load, or as shown in the water pump example, or they can include batteries for energy storage, like here, the battery storage. Then when using batteries, charge regulators are included, which switches off the PV modules when batteries are fully charged, and it may switch off the load to prevent the batteries from being discharged below a certain limit. Because if suppose sufficient solar radiation is not there, and battery state of charge is also less, so that it is not sufficient to power the DC and AC loads, then you may go for load curtailment, right? Some loads must be switched off. So that so the basic idea here is to match the generation and demand. But in grid connected system, what is the topology? Grid connected system. In grid connected system, again I'm drawing the PV module here. PV module, it is converted to AC by an inverter. So AC It goes to the distribution board, DB, distribution board. From the distribution board, the local loads are supplied at your home. Local loads are supplied. And from the distribution board, it is connected to the grid also. It is connected to the grid also. So what can be done here? If your load demand is less when compared to the generated power from the PV module, then the remaining power can be injected to the grid, right? So it is supplied to the grid, and if the load demand is more when compared to the PV generation, then some amount of power can be taken from the grid and the load can be fully supplied. So here there is a backup, which is the grid. Okay, so this is the grid connected system. Grid connected system. So the first one was a standalone system. This is a grid connected system. And the third one is a hybrid system. What is a hybrid system? In hybrid system, in addition to the solar PV module, we will have some other source also. So it's a combination of PV and a another complementary method of electricity generation. It can be diesel or gas or wind or whatever. Okay. So in order to optimize the different methods of electricity generation, that means you need to control the power output from each of these sources. PV, whatever is available, we are using it. So the remaining power that is required to feed the load demand, that must be taken from other sources, right? Like diesel or gas-based turbine or whatever, micro turbine or whatever. So the power from each of the units, suppose this is PPV, I have another unit P gas, then another unit P diesel. So this is a diesel generator. This is a gas-based micro turbine. Okay, this is a gas-based. So I have to optimize these three things so that I can feed the load demand. This is the load demand. So PPV plus P gas turbine plus P diesel will be equal to the total P load demand. If it is not grid connected, then no grid is involved here. Otherwise, there will be P grid also. But here I am considering a standalone hybrid system. Okay, then that will be equal to P load. Now, when you use these components, and when you use the network itself to power the load, then the network will have some losses, right? Network will have some P loss. So that should also be supplied from the source. So here it's not only P load now, P load plus P loss. P load plus P loss must be supplied by all these sources. So this is what is a hybrid system. Now, let's see how a PV system is designed. Okay, PV system is designed. We'll see some examples. So an approach for designing. First, we'll do for off-grid systems. That means not grid-connected systems. Okay, designing off-grid systems. Approach for designing off-grid systems. So what is the first step? The first step is determine the total load current and operational time. Total load current and operational time. Operational time in the sense the time during which the load should be operated. Now add system losses. System losses. So what is done is total load current, if it is represented in amperes, if you know the operational time in hours, then you should get the ampere hour. Okay, you should get the ampere hour. Then this is for concerning the load only, but we have losses also to be supplied from the source. So you have to add system losses, right? Now in the third step, determine the solar irradiation. Solar irradiation in daily equivalent sun hours. Daily equivalent sun hours, or ESH. We'll see what is that ESH. Now, the last step or the fourth step is determine the solar array, total solar array current requirement. Solar array current requirement. 6 steps are there. Okay, fourth one is determine the total solar array current requirement. Then the fifth one is optimal module arrangement. How to arrange it in series parallel combinations, as we have seen. How many should be in parallel, how many should be in series, what is the number of what is the number of cells in one string, like that. So optimal module arrangement. Then the sixth one is battery size. Determine the battery size. Okay, determine the battery size. So these are the steps. Now let's see with a simple example how we are going to do this. Okay, so the first step. Okay, so I'm giving you an example here. A 12-volt PV system is given. A 12-volt PV system. It should have two DC appliances. It should power two DC appliances, A and B. Okay, A and B. A requires 15 watts. B requires 20 watts. Now, the average operational time per day is given as, for A it is 6 hours, for B it is 3 hours. Okay, now you are asked to find the daily energy requirement of the device expressed in ampere hours. Daily energy requirement. So let's see. Device A. What is the wattage? What is the wattage of device A? What is the wattage? Anybody? It is given in the question, right?
90 watt or
no, for A it is 15 watts and B it is 20 watts. So 15 watts is the wattage of device A and it is operational for 6 hours. So I'm converting it to watt hours. So 90 watt hours. Okay. Now for device B, 20 watts is the power requirement or wattage. Now 3 hours is the operational time. So 60 watt hours is the energy requirement of device B. Now, what is the total energy requirement? Total energy requirement. What is the total energy requirement? We have to power both A and B, right? So 90 plus 60 will give you 150 watt hours is the requirement, total energy requirement. Now, I want to convert this watt hours to AH, right? Daily energy requirement in AH is what is asked, or the ampere hours is what is asked. So from this 150 watt hours, I need the voltage. What is the voltage? Standard voltage of the PV system. It is given 12 volt PV system, right? So 150 watt hours divided by 12 volt. So this is a DC system. We are dealing with a DC system. So watt hours, basically what it means is VAH. Volt ampere is equal to watts here, because it's not an AC system, it's a DC system. So this will give you energy requirement in AH. What is the value here? What is the value? 12.5. So 12.5 AH is the daily energy requirement that you should, feed. The energy requirement is this much. So the energy that should be fed from the solar panels is 12.5 AH. Now, instead of taking DC loads, if I want to take AC loads, then what should be considered in addition? because we have another component coming in into picture, which is in between PV panel. This is panel, okay, and load. This is my load. I have an inverter, right? I have an inverter which converts DC to AC, so that only I can, so that I will be able to feed the AC load. So I have to take the efficiency of the inverter into consideration. You can use thumb rule here. A standard efficiency of an inverter, you can use it as 85%. It may vary, but you can assume, for now you can assume this as the efficiency, 85%. Now, what is the difference in finding the energy requirement in terms of AC loads? We'll see. So with the same thing, we'll use the same loads. We'll see some, the same loads we have, but in addition we have some AC loads also. So we have a computer, okay, computer, which is device C. Now we had already used A and B, which are DC loads. Now I have another load. This is load C, which is computer, which is AC, and a TV set, which is my load D. Okay, both are connected to the PV system. Now the computer has a rated power of 40 watts and it runs for 2 hours per day, because we are doing everything in daily, in terms of daily energy requirement. So 2 hours per day, and the TV set is of 60 watts and it works for 3 hours per day. Okay, now you are asked to find the daily energy requirements of the devices expressed in DCAH. Expressed in DCAH. Why it is asked expressed in DCAH? Because if you are just finding it from in terms of AC, that means you are dealing with the output side of the inverter, right? Output side of the inverter is AC, right? But you need to find in terms of DC side. That means the output of the panel. From this side you have to deal with it. So you need to consider the panel, inverter efficiency. If you use the inverter efficiency, then you can come to the input side from the output side. So let's see how it can be done. Now, what is the wattage of device C? Device C, anybody? What is the wattage of device C? What is the wattage of computer? 40 watts. Now, if I want to find watt hours for this device, then 40 watts into 2 hours, right, which is 80 watt hours. Then for device D, that is the TV set, I have 60 watts as the rated wattage, and it works for 3 hours, which is equal to 180 watt hours. Okay, now my total energy requirement is 180 plus 80, which is equal to 260 watt hours. So 260 watt hours is the AC energy requirement, right? That is at the output side of the inverter. I have an energy requirement of 260 watt hours, but my inverter efficiency is only 85%. So at the input side, I need more energy. At the input side of the inverter or at the output side of the panel, I need more energy. So how will you find it? 260 watt hours divided by 0.85. So that will give you 306 watt hours. That will be the output watt hours at the panel output side. That means the input side of the inverter. This is the inverter. This is the panel. Okay.
Sir,
now,
TV set you took as DC?
No, TV set I took as AC.
Sir, both AC you took. Okay,
both AC, both AC. Because see, in the first case I took both as DC. In the previous problem, in this problem I am taking both as AC to show the importance of inverter efficiency. Okay, that is my load A and B. Loads A and B are DC. Okay, my loads C and D are AC. Okay, so here later we'll add everything. Okay, now I am segregating it as AC load and DC load. So now it is 306 watt hours. Now how will you find in AH? How will you convert this to AH? Now we have reached the output of the solar panel, right? So we know that the rated voltage is 12 volt, right? So if you know the 12 volt rating, then 306 watt hours divided by 12 volt will give you 25.5 AH. That should be produced by the solar array. Okay, from the solar array you need this much. So basically for DC loads we have found what was the answer for DC load? Let's see.
12.5.
12.5.
12.5. Yeah, 12.5. And for AC loads, I need 25.5 AH. So that now my total AH requirement is 12.5 plus 25.5 AH. Accordingly, I have to use the use the capacity of the solar array. But here system losses are neglected as of now. Suppose I want to add the system losses also, and suppose the system loss is 20%, then 12.5 H
$45.6.
45.6 H. 45.6 H. Okay. So this is how we do it. Now, so finding the AH requirement from with respect to AC loads and DC loads. So as of now, I'll do one thing. I'll stop here and we'll continue in the next class. 1 minute. Let me stop recording.